Hello everyone. Today I am going to discuss about Module 5. First we will see what are the topics we are going to get in Module 5. So the first topic is 555 timer. We want to study about 555 timer. Then types of 555 timer. Then PLL, that is phase locked loop. Then we will discuss about DAC, and finally so we will discuss about 723 regulator. It's a voltage regulator. So today, so we will discuss a 555 timer. So that is internal block diagram of 555 timer. In the lab session, I have explained about 555 timer. It's an IC version. It contains 8 pins. So 1, 2, 3, 4, 5, 6, 7, 8. So first we will study the internal block diagram of 555 timer, and so in that internal block diagram we will try to identify the pins. Okay, so this is the 555 timer block diagram. So basically 555 timer is actually called as what? A non-sinusoidal oscillator. Oscillators, in the oscillators there are two different types of oscillators. One is sinusoidal oscillator, another one is what? Non-sinusoidal oscillator. So this is the best example for a non-sinusoidal oscillator. It will going to produce actually square wave. Except a sine wave, so it will going to produce what? Square wave. So this belongs to a non-sinusoidal oscillator. Now here this 555 timer, it is divided into 4 different stages. So this is the first stage. You take any type of multivibrator, whether it may be astable, monostable. Basically there are 3 different types of multivibrators are there: astable, monostable and bistable. In the syllabus we are having monostable and astable. Okay. So here it contains 4 different stages. So the first one is what? Charging and discharging circuit. Right now for internal block diagram, this is not required. This indicates what? Charging and discharging circuit. Then we will find a voltage divider network. This is a voltage divider network. It contains 3 5K resistor. First one, second one, third one. That's why it is called as 555 timer, 55 timer. It contains 3 5K resistors. Then in the next stage, it contains 2 comparators. We will see what is the function of comparators. We will see how to generate internal voltage from this voltage divider network later. And it contains flip-flop. So we are using RS flip-flop here. We will see what is the truth table of RS flip-flop. And then we are using a transistor. We will see the operation of transistor also later. So this is the internal block diagram of 555 timer. In the exam, they may ask, explain the internal block diagram of 555 timer, means you should write this circuit. You can write any charging or discharging circuit. So we are having separate charging and discharging circuit for monostable and as well as what? Astable. You can write any circuit here, but you should explain what is the function of voltage divider network, and what is the function of comparator circuit, what is the function of flip-flop, and what is the function of transistor. Suppose if they ask, explain the internal block diagram of 555 timer. Now let us consider, I am not going to consider what charging circuit, we will see it later. I will explain monostable, then you will understand what is the function of this particular circuit. Okay, I will take an voltage divider network. You can see here. So we are using comparator here, and it's actually ideal op amp. And when the ideal op amp, so current flowing through what? Ideal op amp is 0. You already know that. So current flowing through what? Ideal op amp is 0. Hence, if you take this circuit, it simply behaves like a voltage divider network. That means, so it behaves like a what? Voltage divider network. Each resistance value is 5K, 5K, 5K. Hence it is called as 555 timer. You need to find out, you can observe here, this point is actually connected to op amp inverting terminal. Similarly, in this comparator, this point is actually connected to non-inverting terminal of what your op amp 2. So what you should do here, you should find out what is the voltage across this point and what is the voltage across this point. Normally this is upper threshold point, we say. This is lower threshold point, we say. Nothing but control voltage. This is pin number 5. Pin number 5 is control voltage. Before that, we will identify the pins in this block diagram, in the internal block diagram. So this is actually pin number 1. So pin number 1 is nothing but ground. You just recall, the IC configuration. You will come to know what all the pins are available and what is the function of those pins. So pin number 1 is actually ground. It's a circuit ground. Then pin number 2, it's actually trigger. We are applying pin number 2 to the comparator circuit, and that is nothing but inverting terminal. This is trigger, nothing but an input. Then coming toward pin number 3, pin number 3 is nothing but your timer output, 555 timer output. Pin number 4 is associated with flip-flop, so that is reset pin. Then pin number 5, as I said, it's a control voltage. It is internally generated by what your voltage divider network. You need to find out that voltage. That control voltage you can also call it as lower threshold point. Then pin number 6 is it's actually threshold voltage. This is control voltage. Pin number 5 is control, and pin number 6 is what? Threshold. Again, I will tell you, pin number 6 and pin number 2 are nothing but what? Inputs. Okay, so pin number 6 is threshold. Then pin number 7 is actually this one. It's a discharging pin. It is always connected with a transistor. So we will see. So what is the function of this pin? So we will see later. This is pin number 7. Now pin number 8 is nothing but what your supply, that is VCC. And here VCC will going to vary from 4.4 volts to 15 volts. You can apply voltage from 4.4 volts to 15 volts. I think in the lab, so we kept 5 volts. Normally we go for 5 volts. Now let's try to understand the internal block diagram of this 555 timer. As I said, it contains 4 different stages. This is the first one. This is the first one, this is the second one, and this is the third one, and this is the fourth one. That means the charging and discharging circuit, that is stage 1, then voltage divider network, that is stage 2, and the comparators, that is stage 3, and flip-flop, that is stage 4. Now let's try to find out what is the voltage across this point. That is nothing but VTH, upper threshold point, and we'll try to find out what is the voltage across this point. That is nothing but control voltage, that is nothing but lower threshold point. So as I said that in the ideal op-amp, current flowing to ideal op-amp is 0. If that is the case, we can find out what is the voltage across this point and this point. It's a simple voltage divider network. I can draw a separate circuit like this. So I just want to find out what is the voltage across this point. You all know how to find out VTH now. I just want to find out voltage across these 2 resistors. If you see these two resistors are connected in series. If that is the case, I want to find out VTH, voltage across these 2 resistors. That means 5K plus 5K, it will become 10K divided by total resistance in the branch. That is nothing but 15K multiplied by VCC. That means 5 2s are 5 3s are. So what is the voltage we are going to get? 2 by 3 VCC. That is nothing but VTH. Now this VTH is connected to negative terminal of the op-amp. So in the negative terminal of the op-amp, you are going to get how much? 2 by 3 VCC. You should understand how to get this 2 by 3 VCC. Just by applying voltage divider network to this voltage divider circuit, we are going to get 2 by 3 VCC. We got voltage across this point. Next, you need to find out what is the control voltage. As I said that the control voltage is nothing but internal voltage. So we are going to get from voltage divider network. Let us try to find out what is the control voltage or what is lower threshold voltage. Again, very simple. It's a simple voltage divider network. I just want to find out voltage across this particular resistor, that is nothing but VTL, lower threshold voltage. How to find out lower threshold voltage? VTL will be equal to this resistance, that is nothing but 5K, divided by total resistance, that is 15K, multiplied by VCC. 5 1s are 5 3s are, that is nothing but 1 by 3 VCC we are going to get. You remember, to find out voltage across this point VTH of upper threshold voltage, you need to consider these 2 resistors, 5K plus 5K divided by total resistance. But while finding voltage across what? Only 5K, you need, that is nothing but your lower threshold voltage, that is nothing but your control voltage. You need to consider only this resistance, 5K divided by 15K into VCC. You will be getting 1 by 3 VCC. Again, this 1 by 3 VCC is applied to positive terminal of whatever comparator 2 or nothing but op-amp. This is all about voltage divider network. From the voltage divider network, we are going to get voltage across this point, that is VTH, and we are going to get control voltage, that is internally generated by whatever voltage divider network. So that is 1 by 3 VCC. We got 2 by 3 VCC and 1 by 3 VCC from voltage divider network. Very simple. Apply voltage divider rule, you will get those two voltages. Now the next block is comparators. You can see here, I have explained already. Whenever if you operate op-amp in an open loop configuration, because of high open loop gain, op-amp output will saturate. Again, so we are going to get positive saturation and as well as what negative saturation. Depending upon the input, we are going to get positive saturation and negative saturation. Now, this op-amp will act like a comparator because we are applying two different voltage to the negative and as well as what positive terminal. That means we are applying two different voltage for inverting terminal and as well as what non-inverting terminal. Basically, you know the definition of an op-amp. Op-amp, it will going to sense the difference between two input signal. That is, V0 is proportional to, it is directly proportional to the difference between two input signal. That is V2 minus V1. Suppose if I remove this proportional, then it is equated to some gain where A into V2 minus V1. So this A is nothing but open loop gain. That open loop gain is very high. Because of that high open loop gain, we are going to get saturation. So depending upon the input, say for example, if V2 greater than V1, when V2 is greater than V1, this indicates voltage across non-inverting terminal is more than inverting terminal. If that is the case, we are going to get positive saturation. Similarly, when voltage across non-inverting terminal is less compared to inverting terminal, in other words, voltage across inverting terminal is more compared to non-inverting terminal, we are going to get negative saturation. So, when V2 is greater than V1, we are going to get positive saturation. When V2 is less than V1, we are going to get negative saturation. In binary, this is what your digital. In binary, it is represented as what? In digital logic, it is represented as 1 plus VSAT is represented as 1 and minus VSAT is represented as what? 0. You should remember this point. It is very, very important point at this point. Okay, so this is all about whatever comparator. So comparator, we are operating in an open loop configuration. Whenever if you operate op-amp in an open loop configuration, it will saturate. Depending upon the input, it will give positive saturation and it will give negative saturation. Now coming to what transistor operation, what is the next stage? The next stage is what? Flip-flop. In the flip-flop, you should understand, so we are using RS flip-flop and you should understand what is the truth table of RS flip-flop. So here, again we are having two inputs, that means we will be getting four different combinations, 0, 0, 0, 1, 1, 0, 1, 1. So here I just need only two combinations. What are those two combinations? 0, 1 and 1, 0. R indicates, you remember, R indicates reset pin, S indicates set pin. And one more thing, this flip-flop is nothing but sequential logic circuit. Sequential logic circuit means where output is depending upon present input and as well as what? Previous output. That is one point. And flip-flop is actually it's a bistable circuit. That means it contains two states. One is logic 0, another one is what? Logic 1. Q and Q bar. It contains two different states. And one more thing, the output of a flip-flop is always complementary. That means if Q is equal to 0, definitely Q bar will be equal to 1. Always output of a flip-flop is complementary. You will not get like 0, 0 or 1, 1. It is always 0, 1 or 1, 0. Okay, that means it's a complementary. Output of a flip-flop is complementary. Now if you see the truth table of RS flip-flop, so we are having four combinations. Again I am repeating, we don't want four different combinations. We just need only two combinations, that is 0, 1 and 1, 0. When R pin, reset pin is equal to 1, we will see what will going to happen. When set pin is equal to 1, we will see what will going to happen. See here, when it is 0, 0, it will going to acquire previous stage. It will not, output will not change. It remains same. Suppose if the previous output is 0, 1, it will retain 0, 1. If the previous output is 1, 0, it will retain 1, 0. And that is what I said, it's a sequential logic circuit where output is depending on present input and as well as what? Previous output. Here, output is depending upon previous output. For which case? For 0, 0. Again, I don't want that condition anymore. So 0, 1, when 0, 1 means here set pin is equal to 1. Always you remember, if set pin is equal to 1, Q is always 1. So Q value will be equal to 1. Similarly, if reset pin is equal to 1, in the next condition, reset pin is 1. When reset pin is equal to 1, always you remember Q bar will be equal to 1. So you should remember these two conditions. And when it is 1 1, we are going to get output as a 0 0 or 1 1. This is actually invalid. So this condition will not exist in the case of flip-flop. You will not get this condition. So here we'll consider these two conditions, 0 1 and 1 0. When set pin is equal to 1, Q is equal to 1. When reset pin is equal to 1, Q bar is equal to 1. You should remember this truth table. In the analysis, these two conditions are very, very important. So this is all about what your flip-flop. Now there is one more thing is left. This the output of flip-flop Q bar is actually connected to the transistor. We will understand what is the operation of transistor. Normally you take a transistor, it will behave like a switch and it behaves like an amplifier. Here transistor is used as a switch. Let's try to understand how transistor can be used as a switch. Very simple. When the input voltage is greater than VB, where VB stands for forward voltage, nothing but cut-in voltage. If you take a silicon transistor, this is NPN transistor. You take a silicon transistor. For silicon transistor, forward voltage is 0.7. When VA is greater than 0.7, this transistor will turn on. So transistor is on and it acts like a short circuit like this. This indicates what? Short circuit. Similarly, if VA is less than VB, when VA is less than 0.7, you take a silicon transistor, when VA is less than 0.7, it acts like a open circuit. At that time, Q is off. That means transistor is off. This is open circuit. So this is the condition of a transistor. So this is the internal block diagram of what 555 timer. You should understand if you want to design any applications based on 555 timer, you should understand the internal block diagram first. Normally we use to design a timer applications, we are going to use 555 timer. You can turn on application for a particular time. You can use what 555 timer. So block diagram, you should understand the block diagram. So I will repeat the block diagram. In the block diagram, it contains a charging or discharging circuit. Then it contains voltage divider network where it contains 3 5K resistors. Hence it is called as what 555 timer. Next it contains 2 comparators. Again, those 2 comparators are operating in an open loop configuration. Definitely we are going to get a square wave. Definitely it will operate in a saturation region. Next it contains flip-flop. In the flip-flop, we are using RS flip-flop. So you should understand the block, the truth table of RS flip-flop, where it contains 4 different combinations. Anyhow, for analysis, we need only 2 conditions, that is 0, 1 and 1, 0. That means when set pin is equal to 1, so Q will be 1, and when reset pin is equal to 1, Q bar will be equal to 1. Then it contains a transistor. Transistor, it will operate in 2 different regions because transistor is used as a switch at this point. So when VA is greater than VBE, transistor will turn on, it acts like a short circuit. It is on actually. When VI is less than VBE, transistor will operate in a cutoff region. It acts like a open circuit. At that time, transistor is off. So this is the internal block diagram. In the exam, definitely they are going to explain the internal block diagram of a 555 timer means you should explain this much. Thank you.